Welcome to another episode of Code for Thought. The guest for this episode is Nick Radcliffe. Nick is wearing not one or two, but three hats. One as an entrepreneur for a commercial company, one for the Smart Data Foundry, a non-commercial non-profit organization, and the third for the University of Edinburgh, where he's a visiting lecturer. What the three hats have in common is data analysis and data science, and Nick's effort to make people aware of the importance of verifying data quality for your machine learning applications, or really for anything else. Which brings us to one of the central themes for this episode, test-driven data analysis, or tdda for short, which is also the name for the Python library Nick has been working on. The software engineers amongst you may be aware of test-driven development, the principle that before you start writing code, you think about how to test it, and then go and write the tests. In this episode, I want to find out from Nick what's behind test-driven data analysis. How does it work in practice? And what does his Python tdda library bring to the table for data analysts and scientists? But before we go into it, here are the usual shout-outs. We have a hot autumn of conferences coming, as I'm sure you have heard by now. First, the UK RSE conference with satellite events in Swansea between the 5th and the 8th of September. Then the German Unconference in Jena between the 26th and the 28th of September. And if that isn't enough, there is another interesting day on Hidden Ref in Bristol on the 21st of September. So look up the conferences from the episode notes, and if you like to volunteer, give the organizers a shout, please. As for the US RSE conference, the first face-to-face conference in its kind in Chicago between the 16th and the 18th of October, there will be further announcements coming along shortly. But now back to my conversation with Nick. Hello, Nick. Welcome to the show. Thank you very much for your time. We're going to talk about test-driven data analysis today. But before we do, could you quickly introduce yourself, please?
Yes. Hello, Peter. Thanks for inviting me. My background is a mix of sort of all the things maths and physics and computing and AI, and I guess what we now call data science. I have three main hats. I have my own company, Stochastic Solutions, which is a data science company that both produces software, including the tdda library, and I guess we make our money by doing analysis and consulting for people. I'm a visiting professor in the maths department at Edinburgh, though I don't visit all that often. And I'm the chief data scientist for the Smart Data Foundry, which is a non-profit company owned by the University of Edinburgh that tries to unlock the power of private data for public benefit.
And you're a musician, because I'm sorry if I did mention that, but I see we can see each other on Zencast, and I see a lot of guitars and musical instruments at the back.
Guitar is very important to my life. That's not to say I necessarily am a musician, but I play.
Okay. Well, let's go back swiftly then to test-driven data analysis. So people might be familiar with test-driven development, which is a concept that's come up as part, I think, of the agile software development movement. But test-driven data analysis, what is that?
So where it came from was my long-term collaborator, Patrick Surrey, came in one day, and we'd been doing test-driven development for ages, and he said, we do test-driven development. Shouldn't we do test-driven data analysis? And we sort of, exchanged looks, and it was completely obvious that's what we should be doing. But neither of us had any idea what test-driven data analysis could be. It just seemed that data analysis was a much messier, less structured process than development. I've spent a lot of the last, 7 or 8 or 10 years or something trying to answer that question. And the way I normally describe it now is that it's an attempt to extend the ideas from test-driven development of testing for software correctness, which I think is really the core of TDD, with things that are also important for data science, data analysis. So testing for, ideally, the meaningfulness of the analysis, the correctness and the validity of input and output data, and ideally also the correctness of interpretation, though that's more difficult. But in practice, it mostly comes down to two things. One part is trying to extend this idea of testing to data analysis code and data analysis processes with things I call reference tests, and to some extent with automatic test generation. And then the second thing is validating data using constraints and indeed automatically developing suitable constraints for checking data.
I'd like to see how it all comes together, because I think in test-driven development, the idea is that you write the test before you can actually start developing the code. Or, I mean, that's the theory.
That's the theory. Yeah.
Whether people actually do that or not is another question. How does it work then in test-driven data analysis? How does the workflow then work?
Almost certainly not like that. One of the things that makes testing data analysis type codes more difficult is that you typically can't write the test ahead of time, because your output isn't, it's not like checking that 2 plus 2 equals 4 or that minus 1 plus 1 equals 0 or something. It's, you're producing a graph, or you're producing a table of a million numbers. I guess conceptually you can think about the two different parts. You can think about the reference testing, the bit that extends the normal notion of testing software, as about checking the correctness of your analysis pipelines during the development process, checking that what you produced is correct, and that it continues to be correct if you come back 6 months later and use it again. And in some sense, the data verification checks are more about checking that when you actually use your code, use your data analysis pipeline, that it's processing the sort of data that you expected, and that it's producing the sorts of outputs that you expected, and that nothing's going wrong. So it's more of a kind of live check, I guess, is one way of thinking about how it brings the two things together. But they are somewhat separate parts of both the library and the process.
Yeah, and I think it's quite good that you highlight that, because yes, there is the data pipeline and the testing of the data pipeline, which is the software part. Do the data actually go from A to B, and do they do that in the right format? Or what do you mean by that software part?
When I said at the start, our data analysis didn't feel nearly as structured as the software testing part, I guess the way most data analysis, in my experience, proceeds is that it always starts in the context of at least one concrete data set. No one sits down and writes data analysis code, in the abstract, without having at least some test data of something. And you go through and try to figure out what an appropriate set of methods is and how to implement it. And you at least convince yourself that the answers that you're producing are sensible. Now, how formal that is, whether you check it against something else, whether you get a colleague to check it. But typically, anyone who's got any level of diligence will do some form of checking that they're happy to produce the outputs. And so at that stage, you've got at least one data set that you can push through your data analysis pipeline, and you've got a set of results that you believe are good enough. The idea of a reference test is that whereas people tend to emphasize unit tests for software development, checking individual functions as the most important thing. And yeah, there are integration tests and system tests, but most people emphasize unit tests. The idea with a reference test is that it's much more a full system test. And it's saying, well, at the very least, let's check that if you take the same data that you use to develop your system and you pass it through your analysis pipeline, that you produce the same answers. In order to turn that into something testable, what you have to do is you have to collect your inputs, which will usually be in a file. You have to try and, as much as possible, script your process. So if it's a thing that involves, a recipe where you have to do 8 separate things, ideally script that so that it becomes automated. Sort of the most interesting part is you have to develop some kind of a verification procedure. So what we'd normally think of as a diff procedure that says, well, are the outputs what I expect the outputs to be? The difficulty with that is, in my experience, most of the time, the outputs that we produce from complex data analysis pipelines are not identical. They don't produce exactly the same files or exactly the same screen output each time. For, trivial reasons, like they include a date stamp or they include the version numbers of various components of the software. And so what you're really interested in is, in some sense, the semantic correctness of the output rather than what you might think of as the syntactic correctness. It doesn't have to be the same file, but it has to be the same graph, or it has to be the same set of numbers or whatever.
I think in machine learning, it's also that you actually handle a lot of data frames or matrices from one node to the other. And is it also then a question of making sure that they come in the right format so that the whole system doesn't fall over?
Certainly that they come in the right formats. That's more the data checking part. One of the things people often think when I talk about this, that it's either to do with random numbers or to do with numerical rounding. And there's some truth in that, but numerical accuracy, actually, if you run the same calculations on the same hardware or even on different hardware these days, you will tend to get exactly the same answer. That's less true if you run in parallel, because if you run in parallel, then potentially operations happen in different orders according to exactly where a job gets allocated. And then if you sum a sequence of numbers in two different orders, you will get different numerical rounding. So that can be an issue. And in terms of random numbers, you can fix the seed. Again, that becomes more difficult if you're running in parallel and different processes depending on timing. But you can handle a lot of that.
You mentioned constraints. Could you describe a little bit more about by what you mean by that and how that works?
If you have deterministic processing, then you should be able to do exact checks. But it's also true that if you are allowing the seeds to vary or you've got parallelism that affects the things, there are still things that ought to be true. So your types still ought to be consistent, for example. If you're producing probabilities, they probably ought to be between 0 and 1, for example. If you're producing if you're producing indexes for records, they ought to be in the range of indexes that exist. With the data checking bit, the concept is, in principle, you could, and this is for input data and output data and potentially data stages in the pipeline as well. There are a whole lot of things that you would know ought to be true about it. So you expect your input to have these fields, for these fields to have these types, for there to be particular ranges. If it's human ages, you probably expect them to be between 0 and 130, or maybe if they're adults between, 18 and 65 or whatever. And if you get 4 million, that's almost certainly a problem. You've got nullability. Is this value allowed to be null? If this is a key field, is it allowed to have repeats? So you could just ask people to write down a set of things that they believe ought to be true of the data. That tends to be a very bad way to go because no one really likes being faced with an empty sheet and, just write down all the things you know. So instead, we use not so much machine learning, but a machine learning kind of approach where we just say, give us some data that ideally you've checked is good data. You've at least looked at and asserted is vaguely sensible.
A good test data set.
Yeah. And then exactly like the stuff that you actually used. And then the tdda library has discover functionality, which will construct a set of constraints that are true for your input data. And so if you verify your input data using the constraints generated from it, it will pass. If your data really was clean, then that should be a good set of constraints for checking further data. The constraints will be quite tight to the data that you produced. So, if we go back to our age example, if actually the data that you checked only had age, the youngest person was 20 and the oldest person was 83, well, it will say, the age should be in the range 20 to 83. So what we'd recommend is that you look at it and you say, well, is that actually right? And people are much happier looking at something that machines produced and saying, let me tweak it. And so you look at that and you say, well, no, actually, it would be fine if it were 18 or it would be fine if it was 16. And, maybe I'm happy to accept any age up to 120 or 130. If you then start using a set of constraints developed like that, and it turns out they're too tight, it's not that terrible because you'll get failures, which will be annoying. But at that point, you can go back and check the failures. The more important thing to check is the other side of it, where if actually you fed it bad data, then you'll get either missing constraints or constraints that are too loose. And that's more serious. So if, for example, your training data had someone who was minus 117 and someone who was 4 million, then the constraints that it'll spit out will say, well, it shouldn't be less old than minus 117. Obviously, you'd look at that and say that's silly. But if you don't catch that, then it's not going to be an effective check. And even more serious, something like if you have a field that shouldn't have duplicates, but it did in your training data, then it won't generate a constraint saying this field shouldn't have duplicates because, it's a primary key. And then it will allow those through. And you'll still probably catch those later, but it will be more, I thought you were checking this data. Why have we got this nonsense coming through? But then you just start using it.
So we have the basic sanity checks, like making sure that the data frame has the right dimensions and that the software actually that handles the data pipeline works. Then we have the constraints to make sure that the data actually are kind of in the range you expect them to be. Mm-hmm. And the third element that you mentioned was the interpretation of the data.
Yeah.
And that is, of course, quite the tricky bit, isn't it? Because how do you codify that? And how do you subject that to testing? Can you actually do that?
I think interpretation is the hardest part. And I think it's the part we've got least far with developing. But it is super important. I think people quite often think that when you talk about interpretation, it's like, it's not that serious, but it can be super, super serious. Two examples that come to mind are, I think it was the Mars orbiter where NASA and ESA collaborated, and ESA was using metric units and NASA was using imperial units. And so they actually lost the mission because they'd interpreted the numbers as being in different systems. Even more straightforwardly and familiarly in a machine learning context, it's really important to know whether you're predicting the positive or the negative case. When it says 99.999%, is that the probability the aeroplane's going to crash or the probability it's going to have a safe mission? Because you really need to interpret
You hope the latter.
interpret that correctly. If you take off, yeah. So that is really hard. I think the data checking part is the bit that helps most with that, but it's still a very long way from what we want. So it can check that you don't get crazy outlying values. And there's lots that we can do by hand, right? So we can label things clearly. We can write out sentences. We can highlight things. We can have, you'll see on a lot of graphs these days, people actually write more is better. And so if you think of it holistically, not just as a software, but as an approach to doing data analysis, it's almost like part of the Hippocratic Oath for data scientists ought to be, we're not going to say it's your fault if you interpret my beautiful output wrongly. We kind of have to say it's our fault if someone interprets our output wrongly, because we should be presenting it in such a way that it's really hard to interpret it wrongly.
Going back to the test-driven development part, where you have a workflow, like, for instance, the workflow of continuous integration, where you submit changes to the code line and then it gets automatically tested. Now, obviously, in your case, this is a little bit more complicated because things may happen at various different stages. So what would a workflow look like, and how could you construct a workflow that can help people using that?
Yeah. And again, I'm sorry, I always have to talk about the two different parts. On the code testing part, that is relatively straightforward. In the case of the library, it has extra methods that you can use with Python's unit test framework that give you new kinds of assertions you can do. The library that we produce allows you to say things like, these two files are equal except for lines that contain this regular expression. Or you can say you have to run it through this pre-processing before you do the test, and you can filter out this kind of thing. Or these data frames ought to be the same, except don't bother checking this column. And so those just fit right in. The other part of it that I guess we haven't talked about is the Python tdda library also includes some relatively new functionality for writing tests for you.
Okay.
That doesn't have to be for Python code. That's for anything that you can run from the command line. So I talked about this idea of reference testing, where you have some code, have an input data set, and the idea that you collect the outputs and write a diff procedure. GenTest offers to sort of take half of that work on for you. So you still have to write the code to do the analysis. You'll have to provide the input data, but you then just give it a command that it can run. When you install the tdda library, you get some command line tools, including tdda. And if you say tdda GenTest and then give it a command to run, like, foo.sh or Python mycode.py or whatever, then what it will do is it will run it a few times. It will look at what's being produced on standard out and standard error. It will look at what files change in the file systems and what gets produced. It will look at how similar the outputs are on different occasions. And then it will write some Python tests for you that check what's going to the screen on the different channels, check what files are getting produced, attempts to put exclusions in so that if different things change or different things seem overly specific to your setup, like if it's got the name of your machine in it, or it's got the path to the directory where you're running it, it will try and abstract those and say, don't worry about that detail, because when someone else runs this, it'll be a different machine, it'll be a different path. But those Python tests can be testing, R code or a shell script or C code or whatever. It can't do anything with GUIs. At least the sort of conventional file system, shell-based stuff, it can do quite a lot with. And those can just fit straight into a CI/CD pipeline. On the data checking part, I think that is different. Obviously, there are one of the things that affects that is whether you're running in batch or whether you're running in more of a sort of real-time scoring kind of a way. So if you're running in batch, you can definitely have the checks just as part of what you're doing. I don't think you typically run those in a CI or CD pipeline, but you can have as just part of wherever you're hosting your thing. We have had prototype stuff for doing stuff in real time as well, but that's not really available in the library. There are some interesting extra challenges if you do things in real time, sort of feeding one case in at a time. Things like checking uniqueness are harder. So it's easy to check the range of a field.
Yeah, because you can go back and check what was there before, but not.
But obviously now if you're saying, we shouldn't have repeated values, well, over what time frame shouldn't you have repeated values? So, things are a little bit different. But we have explored some of those things. In principle, that would be extensions we can do. There's also, we haven't done it, but some databases have constraint capabilities as well. And so another interesting thing would be for the discover process to spit out constraints that the database itself can implement so that you literally can't create the wrong kind of data.
Which databases are we talking about?
I'm not sure. Certainly Oracle and DB2 and things like that have those kinds of capabilities. I don't actually know whether Postgres, which is the database I use most often, has that. I suspect it has some of it.
Now we're going to definitely talk about your Python library because it's been mentioned a number of times and you mentioned some examples. Could you give us an overview of the history of the Python library?
So yeah, tdda, it's a Python library. It has an API that you can use from Python for all parts of it. But it's mostly, when you install it, you get a command line tool that allows you to check data, whatever system you're using, and with Gentest to use. I suppose I often describe it as being a bit like 3 function machines, if you like. So there's a machine that you feed data into, and it spits out constraints that you can use to check data. And indeed, then in another mode, you feed new data and the constraints in, and it spits out failures. One of the most interesting things that the constraint generation stuff can do is it can generate regular expressions for sets of strings. RexPy is the functionality that you can give a set of examples, a set of postcodes to, and it will spit out ideally one or sometimes a few regular expressions that match. And it really should emphasize it's not for free text. It's not going to do anything if you give it War and Peace. But if you give it the sort of data we actually get in data science when it's not free text, a postcode or a national insurance number, a telephone number or stuff like that, it will write correct regular expressions for you, which can be super helpful. And that's a powerful enough bit of functionality that we have a separate tool for doing that. So that's the second function machine. The third function machine, Gentest, is one where effectively you feed code and data in and it spits out tests for you. And then the stuff that you use always from the API is the extensions to PyTest and unit test. What those consist of, as I say, is partly extra kinds of assertions. Another simple thing it does is if you have like 100 files that you want to check, you don't really want to loop over it and just fail at the first file. What you really want to do is check them all and then report which ones failed. There's also trivial extensions it does that are really powerful, like it allows you to tag a test by putting an @tag decorator in front of it, and then to run only the tagged test. Because the tests that we write in data science quite often take longer to run, it can be very important to be able to isolate one test as you're developing something. And I suppose the other thing I should say about the library is it can operate on different sorts of data, not as many sorts as I'd like. You can certainly give it data in CSV files or in fact feather files. It doesn't yet support Parquet files, but it should. But it will also process data in databases and get the databases to do the checks themselves. So I guess what I was talking about previously with databases was some databases have constraints that sort of stop you creating bad data. But what they can all do is execute SQL to report things, and that's what the library does use if the data's in a database.
Could you give us a concrete use case or a scenario where you use that, an example?
Yes. And yet again, if you'll forgive me, I'll give you two, one for each.
Okay, I get 2 for 1. Go ahead.
So on the data checking part, I mentioned I act as chief data scientist at the Smart Data Foundry, which takes data from banks and other financial institutions, de-identified data. It's very strongly governed. We have a safe haven that's not really connected to the internet. And so our information governance team uses tdda. When we receive data, we check the data before it's made available to researchers using exactly this constraint generation and verification stuff to make sure that it hasn't, in fact, got real identifiers like people's names or people's addresses in it. Maybe it will have a partial postcode or something. We'll check it's only got partial postcodes, not full postcodes. And we find stuff all the time. It's difficult for anyone to, provide entirely correct data, and often mistakes get made. And we do the same thing on the way out, that when we produce results, even though we haven't allowed, or we've got checks to ensure that we haven't allowed real identifying data in, we also check on the way out as a belt and braces thing that none has somehow magically appeared in our outputs. But also we obey statistical disclosure rules, so we don't report results from small cells, for example, because that might lead to someone being identified. And so we check that we have obeyed the statistical disclosure rules. On the verification side, so this idea of tdda is quite closely connected with the idea of reproducibility. And that idea of reproducible research is the idea that, in the past, when you published a paper, you just published the paper and that would be it, and people could review it, but all they had was the paper. The idea with reproducible research is that you should ideally publish your code and your data as well, so that other people can run your code or run their own code over the same data. Now, the thing is, we can't do that. the Smart Data Foundry, because the whole point is we can't release the data we've got. It's in a safe haven. It's locked up. Only safe researchers are allowed. So what we quite often do instead is we actually reproduce it. That is, we do 2 implementations, independent implementations, typically in different languages, to produce the same results. And then we check that the results are the same. Again, the embarrassing truth is they almost never are first time, because people make mistakes. And it reveals subtleties, actually. Even when there aren't mistakes, 2 different people interpret the problem differently and end up producing different things. So we then work through very carefully to make sure that ultimately there are either no differences, or at least that the differences are ones we fully understand. So again, the sort of semantic rather than the syntactic equivalence of the outputs. And we use exactly the sorts of checks I'm talking about to check that our results are right before releasing them. So that's another very concrete example of how we use it. And you asked about other libraries as well. TDDA tends to do hard checks on data, that it is in this range. But there's the question of checking distributions, looking for data drift and so forth. So there's a company called Evidently AI that produces things that try to detect data drift. There's a VC-backed company called Great Expectations that produces something quite like the constraint checking part of TDDA, more of an emphasis on writing the constraints by hand than doing discovery, but they have something like discovery as well. And the general testing stuff, I guess I see data science as coming from 2 main traditions, the Python side and the R side, the sort of ML side and the stats side. Many people, particularly from the sort of Python side, have grown up with TDD and therefore bring some of those ideas and try to use them anyway.
The library is pretty easy to install. I guess it's simply pip install tdda.
Pip install tdda, or I guess these days with the number of Pythons people have, Python -m, or you can install it from source. It's available on GitHub under the TDDA account and the TDDA repo.
So where can people read up on TDDA?
So there is a lot. There's documentation at tdda.readthedocs.io. There are a bunch of talks I've given at PyData and reproducibility conferences and so forth, which people can find at stochasticsolutions.com/talks. There's a blog I write at tdda.info. If people are not convinced about needing to run tests and the idea that software will just spontaneously break over time, there's an article on there called Why Code Rusts.
So what's the future for TDDA library then?
That's a good question. I mean, in the short term, the next thing I'm planning to do is add Parquet support, because I think Parquet is becoming more widely used and is a much better alternative to CSVs. In general, the way that TDDA develops is that I implement stuff in our proprietary software first, and then when we've figured out that it's actually useful, transfer it to TDDA. Some of the things that are in the commercial library, but not the open source one yet, not because I want to hold it back, just because they haven't been ready, is things like doing discovery on not entirely good data. So the open source library does assume that the data you've given it is good and generates tight constraints. But it's possible to say, well, it's mostly good, but except that there might be some outliers in there. In which case, rather than generating constraints and then the data that you trained on will pass, some of it will now fail and it will actually find bad data in your original data. There's some stuff for looking at foreign key relations, so trying to figure out whether the relationships between keys from different tables are correct. There's some stuff on dates. So at the moment in the open source library, it checks dates as absolute values. But in the commercial library, it checks relative date ranges as well. So there are lots of little things like that. Gentest can always be improved. RexPy can always be better. And yeah, if we could, I'm not absolutely sure what it would be, but if there's anything I could do to make errors of interpretation less likely, I think that would be a very powerful thing.
One question that just popped into my head now was with, and you mentioned that already early on, was duplication, because very often you get duplication, not in terms of completely identical, but similar enough to know that when a human looks at it, they say, yeah, that's the same thing. So a simple example, for instance, is I worked for a publisher in my earlier career, and often the author name would be entered twice, because then there would be the abbreviation with a dot, the abbreviation without a dot,
right.
Slight misspelling at the end, and then suddenly you get 2 or 3 entries for the same author. How are you dealing with that?
It's funny, I'm dealing with the reverse of that at the moment, actually. I'm doing some synthetic data generation where I'm deliberately generating variations to help people deduplicate in exactly the sense you're talking about. In fact, a very powerful technique is the constraints that it generates are, there are only, I don't know, a dozen different kinds of constraints it generates, min and maximum values, are there duplicates, stuff like that. And so that's fairly limited. And it's interesting. If you look at Great Expectations, they have literally thousands of different constraints that they'll apply. The reason we don't do many of those is that what I find is there are two things that you can do that usually obviate the need for that. One is you can always define a new field that encompasses some extra stuff that you want. So in your case, the sort of thing that you might do is canonicalize a field. If you have your author name example, you try to map the field to some form that is less likely to, that is more likely to exhibit the duplication. So maybe you remove middle names, or you turn all forenames into initials. Maybe you remove all punctuation, all accents. If you have a set of columns that ought to add up to a total, tdda won't tell you that the total's not correct. But if you form a column that's the sum of all the ones that are supposed to make the total, and then subtract that from the total, obviously you end up with something that should be zero. And so it can very easily check that column's zero. The other thing that's super powerful like that is to form derived data sets. You have a set of transactions. You take a set of measurements from them at customer level, for example. Whereas you had a data set that had many rows per customer and different numbers of rows for different customers, and you can only check a few things. If you take some measurements to say, well, how many transactions do people have? And what's the biggest transaction? What's the smallest transaction? Now you've got a whole new table that's got a different structure and a different set of fields. You can apply tdda, you can apply constraint checking to that as well. So those kinds of techniques can help a lot. I'm not sure whether this really answered your question.
It does, actually, because, very often we find that libraries don't provide you with a straight out-of-the-box solution, but with thinking about the problem and coming down to the structure of it and thinking about it in different ways, you can actually use the library to solve it. And I think that's what you just mentioned. I think we've come now to the end. Thank you so much again for your time. That was a very interesting interview. And I wish you all the best for the future and for tdda, of course.
Thank you, Peter. It was great. Thanks for having me. And I hope, whether it's the tdda library or whether it's just the concept of tdda, I hope there's more checking going on, because I think data is quite important.
No, it certainly is, yeah. Yeah, I hope that people will take note of this. Thanks very much. Oh, time's up. See you next time. But before I forget, this podcast is covered by the Creative Commons license. See ya.